maximum subarray. What if I told you there's one simple algorithm that unlocks dozens of tough interview problems? Maximum subarray is a Pattern Mastery 100 legend and shows up in interviews at Microsoft, Amazon, and Google. More than half of candidates overthink it, but once you know the trick, you'll solve it in seconds, no matter how big the array. Let's learn the pattern that makes dynamic programming click. Let's break it down. Given an array of integers, both positive and negative, we're looking for the maximum sum of any contiguous subarray. In other words, what's the biggest slice of the array we can add up? If the whole array is negative, pick the least bad number. Now let's assess. A brute force approach checks every possible subarray, n squared time. That won't work for big inputs. But what if, as we scan left to right, we keep a running total? If that total ever goes negative, we start over, since a negative sum can only hurt us. This is the magic of K-Dane's algorithm. At each position, decide if you're better off starting fresh or extending the current sum. Here's the structure. Initialize two variables, current_sum, the best sum ending here, and max_sum, the best overall. Start both at the first number. For each new element, update current_sum as the higher of the number itself, or the number plus current_sum. Update max_sum if current_sum is higher. Return max_sum at the end. Now let's try to implement it using solution 1. We're defining a function called max_subarray that takes an array nums. We store the length of the array in n. We create an array called dp of size n, filled with zeros. dpi will represent the maximum subarray sum that must end at index I. We set dp0 equal to num0, because the best subarray ending at the first element is just that element itself. We create maxSum and set it to num0, because that's the best sum we've seen so far at the start. Now we loop from I equals 1 up to n-1. At each index I, we decide whether we should start a new subarray at nums I, or extend the previous subarray. So we set dpi to the maximum of the current number nums I, or the previous best ending sum dpi-1, plus nums I. After we compute dpi, we compare it with maxSum. If dpi is bigger than maxSum, we update maxSum. After the loop finishes, we return maxSum as the largest subarray sum. Time complexity is O of n because we scan the array once. Space complexity is O of n because we use the dp array. Let's verify solution 1 for maximum subarray. Input is nums equals -2, 1, -3, 4, -1, 2, 1, -5, 4. We start with dp0 equals -2, and maxSum equals -2. At I equals 1, we choose between starting at 1, or extending -2 plus 1 which is -1. We pick 1, so dp1 is 1, and maxSum becomes 1. At I equals 2, we choose between -3 or dp1 plus -3 which is 1 minus 3 equals -2. We pick -2, so dp2 is -2, and maxSum stays 1. At I equals 3, we choose between 4 or dp2 plus 4 which is -2 plus 4 equals 2. We pick 4, so dp3 is 4, and maxSum becomes 4. At I equals 4, we choose between -1 or dp3 plus -1 which is 4 minus 1 equals 3. We pick 3, so dp4 is 3, and maxSum stays 4. At I equals 5, we choose between 2 or dp4 plus 2 which is 3 plus 2 equals 5. We pick 5, so dp5 is 5, and maxSum becomes 5. At I equals 6, we choose between 1 or dp5 plus 1 which is 5 plus 1 equals 6. We pick 6, so dp6 is 6, and maxSum becomes 6. At I equals 7, we choose between -5 or dp6 plus -5 which is 6 minus 5 equals 1. We pick 1, so dp7 is 1, and maxSum stays 6. At I equals 8, we choose between 4 or dp7 plus 4 which is 1 plus 4 equals 5. We pick 5, so dp8 is 5, and maxSum stays 6. We finish the loop and return 6. The output is 6, and the expected is 6. They match, so solution 1 is correct for this test case. Let's try to implement it using solution 2. We're defining a function called max_subarray that takes an array nums. We create max ending here and set it to num0. This represents the best subarray sum that must end at the current position. We create max so far and set it to num0. This stores the best subarray sum we've seen anywhere so far. Now we loop from I equals 1 to the end of the array. Inside the loop, we store the current number in x. We update max ending here by choosing the better option, Either start fresh at x, or extend the previous subarray by doing max ending here plus x. So we set max ending here to math.maxx, max ending here plus x. Then we compare max ending here with max so far. If max ending here is bigger, we update max so far. After the loop ends, we return max so far as the maximum subarray sum. Time complexity is O(n) because we scan the array once. Space complexity is O(1) because we only use 2 variables. Let's verify solution 2 for maximum subarray. Input is nums equals 1. We start with max ending here equals 1, and max so far equals 1. The loop starts at I equals 1, but the array length is 1, so the loop doesn't run. We return max so far, which is 1. The output is 1, and the expected is 1. They match, so solution 2 is correct for this test case. Let's recap maximum subarray. This problem is a classic because it looks simple, but it really tests whether you know how to make the right decision at each step and still get the best overall result. The task is to find the maximum sum of any contiguous subarray, the best continuous slice you can take from the array. The challenge comes from negative numbers, because they force you to decide when continuing a subarray helps and when it starts dragging the total down. We compared approaches and quickly saw brute force would be too slow since it tries every possible subarray. The key insight is the pattern behind K-Dane's algorithm. If your running sum ever becomes negative, keeping it only hurts future totals, so it's better to reset and start fresh from the next position. The solution structure relies on 2 trackers, one for the best sum ending at the current position, and one for the best sum seen overall. As we scan the array, we decide whether to extend the current subarray or restart at the current number, and after each decision we update the global maximum if the new running sum is higher. We implemented the approach successfully on LeetCode without errors by processing one element at a time and making that simple restart or extend decision. The logic stays minimal, but it captures exactly how you'd reason through the problem step by step. We validated correctness with LeetCode test cases. On the sample input, -2, 1, -3, 4, -1, 2, 1, -5, 4, the algorithm correctly produced a maximum sum of 6, matching the expected output. We also confirmed it behaves correctly on edge cases like a single element array such as 1, where the result is 1. The takeaway is that strong optimization often comes from knowing when to let go of a bad run. K-Dane's algorithm works because smart local decisions, restart when the sum turns negative, build into the best global outcome, and that mindset carries into many dynamic programming problems.